In this example, it looks like we have a pretty interesting trigonometric identity that we would like to verify. On the left side, we have this fraction underneath a square root, and it looks like this fraction is 1 plus sine x over 1 minus sine x, so a lot of similarities here. On the right side here, it actually looks like we have an absolute value in the denominator, so very interesting. Well, right off the bat, I remember that there is a nice property that relates square roots with absolute values, and I want to go ahead and share that with you real quick. So if we take the square root of x squared, we know that that's the absolute value of x. Okay, so that's a property that we would like to keep in the back of our mind as we work at verifying this trigonometric identity. Okay, so how can we get some squares underneath this radical so it ends up giving us an absolute value? Well, I'm going to go ahead and do a thing. Well, I'm going to actually work with this left side and make this left side look like the right side. And that's how we're going to verify this identity. And so what I'm going to do inside this square root here, since I have this fraction, I'm going to go ahead and multiply the top and the bottom by the conjugate of the denominator. Okay, so let me go ahead and set that up, and this will be a long radical bar there. So we have the 1 plus sine x right here, and that's over the 1 minus sine x. I'm going to go ahead and multiply, like I said, by the conjugate of the denominator. So 1 plus sine x, 1 plus sine x. Okay, and so that's equivalent to my right side. And so I'm just going to go ahead and put parentheses around everything so there is no confusion as to what's going on. Now in the numerator, it looks like 1 plus sine x times 1 plus sine x. Well, I can just write that as 1 plus sine x squared. And that's going to be over, so 1 minus sine x times 1 plus sine x will give me 1 minus sine squared x, and of course all of that is under that square root. Okay, well, let me go ahead and come over here and write another property down because I see right here this 1 minus sine squared x. So I also know that sine squared x plus cosine squared x equals 1. That's a Pythagorean identity. So I'm dealing with 1 minus sine squared x. So if I go ahead and subtract sine squared x from both sides, I have cosine squared x equals 1 minus sine squared x. Okay, so this is what I have in my denominator. So I can go ahead and replace that with a perfect square here, this cosine squared x. So let's go ahead and do that and see what we have. Okay, so I'm going to go ahead and split this fraction up into a radical of the numerator and a radical of the denominator at the same time. So here's what I have. 1 plus this sine x, this is squared and under the radical, over, and we have the square root here of cosine squared x. Okay, so it looks like underneath both of our radicals we have perfect squares. And that's fantastic because now we can use this property right here. So underneath the radical is a perfect square, so it just changes into the absolute value of the x, or whatever this base is. So I can now exchange this for the absolute value of 1 plus sine x over the absolute value of cosine x. Well, this is not exactly what we're shooting for, because if you come up here, this is just 1 plus sine x over, then the denominator has the absolute value of cosine x. Notice there is no absolute value in the numerator. So how can we go ahead and just get rid of the absolute value here? It almost seems like it's willy-nilly. They just did it because they didn't like it there. What's the reasoning, or what's the justification here? Okay, well, let's take into consideration what's inside these absolute value bars. It's a 1 plus sine x, and I'm going to go ahead and move over just a little bit. So 1 plus sine x, and it's the absolute value of that is what we have. Okay, so if we think about sine x, what are all the possible values that I could get when I take the sine of some angle? Essentially, I'm asking, what's the range? So the range is any value from -1 up to 1 inclusive. So -1 is the smallest value I can get with a sine, and +1 is the largest value I can get when I take the sine. Okay, well, I have this 1 plus, okay, so what's the worst case scenario? So I have a -1, so 1 minus 1 is 0. So what are all the potential values I could have in here? Well, 0 up to 2. And that's it. Those are all the values that I'll have inside this absolute value. If that's the case, is there anything that's ever going to be negative? Well, no. So since there are no negative values, I don't need to concern myself with taking the absolute value, because all of these values will be non-negative to begin with. So instead of having the absolute value, I don't really need to have it there. So I can just kick it out. So 1 plus sine x over the absolute value of cosine x. And here now is my finished trig identity. And so we do need the absolute value bars in the denominator because the range of just the cosine function is the same, -1 to 1 inclusive. So this could result in a negative, so we do need to contain those absolute value bars down there. So let's go ahead and kind of recap what we did. So we started up here. We noticed that we had a square root and an absolute value in this trig identity, which looked maybe a little tricky. But we did know this property here. The square root of x squared is really the absolute value of x. Okay, so inside this radical, we went ahead and multiplied the top and bottom by the conjugate of the denominator. And that was nice because we set up here a perfect square, and we set up here a Pythagorean identity which could turn into a perfect square. So then I was able to take away the square roots because I canceled with the perfect squares, and I had the absolute value in the numerator, absolute value in the denominator. But of course I saw that the absolute value in the numerator was not necessary because the only values I was going to get were non-negative anyway. So here then is how this simplifies, and once again that's exactly what we needed it to look like to verify this trigonometric identity. So there's that example.